The notes on seismic waves, the waves that are generated by earthquakes. So, every year all around the world, there are earthquakes. What you're looking at here is 35 years of data. So earthquakes do not occur randomly, spread out evenly around the world. They are very, very concentrated in sort of clusters. It looks almost like a swarm of bees around a hive, right? And one of those places is right here, California. Okay. Another cluster you might notice is the west coast of South America. I mean, I can't even see that. It's a black blur there. A lot of Europe. And where's Japan? You can't even see Japan on this map. Okay. So this is where earthquakes occur. So what do those places have in common? We'll get to that in a moment. Okay, places like where we live, they have something in common. But first, let's talk about what happens in an earthquake on a very basic level. Rocks are a little bit flexible. Now, you might not think this if you've handled a rock or fallen on a rock. It doesn't seem very flexible. But over larger distances, they actually can bend. Just kind of like you can bend a stick in your hands. You can bend it slightly back and forth, and it'll go back to its original position. That is called rebound. When it goes back to the way it was before, that means it's elastic. But as you know, with a stick, you can only bend it so far, and if you go beyond that point, it'll snap, it'll break. The same thing goes with rocks. You can put forces on them, moving them in different directions, straining them until finally they break. Where they break is called a fault. And contrary to what people think, people are always saying fault lines. Well, they do look like lines on a map. Faults are actually planes, two-dimensional surfaces like a sheet of paper going downward into the earth. Okay, so a fault is actually a plane, a surface, and it is the place where an earthquake has occurred. And usually that's where the next earthquake is likely to happen as well. Once you've made a fault, it makes it much more likely that you'll get another earthquake on the same fault, on the same plane. This is a map of the plates of the earth, the different sections of the surface of the earth, the crust of the earth, or what we call the lithosphere in geology, the part of earth that acts like rocks. Okay? Well, as you notice, some of these plates are big. Like, look at that Eurasian plate. That is huge. North American plate, pretty big. Antarctic plate, pretty big. Pacific plate is very big. This map has a bit of distortion at the top of the bottom. This is a Mercator map. So just notice, well, Greenland isn't really that big. It stretches things out at the high latitudes to make them fit the grid. But actually, the Pacific plate is the largest of all the plates. Okay? And what you notice here is some of them are very tiny. Look at the Caribbean plate. Look at the Juan de Fuca plate. Okay? There's some that are very, very tiny. Okay? The Arabian plate. Now, all of these plates are moving in different directions. And the reason they're moving has to do with convection in the mantle. It has to do with how old they are, the age of the ocean crust, many, many things we don't have time for. But let's just suffice it to say they're all moving in some direction. Sometimes they're moving together, sometimes they're moving apart, and sometimes they're just sliding past each other, just grinding past each other, like two cars going in opposite directions that got too close together and are scraping alongside, so probably breaking off their side view mirrors right there. So watch, if I take this map and transition, watch carefully, to this map. Notice how the locations of all of those earthquakes, looks like a swarm of bees, is on the plate boundaries. So basically you could say that earthquakes generally happen on or near a plate boundary. So earthquakes happen where plates of the earth collide, separate, or slide past each other. So what is an earthquake? An earthquake is just a vibration of the earth produced by the rapid release of energy, and it's initiated by the buildup of tectonic stress. So basically, two different plates moving. Now the focus is where the earthquake really happens. It is the point within the earth where the earthquake starts. Now the focus is always underground. So this is something people misunderstand. A lot of people seem to think the epicenter is where the earthquake happened. But the epicenter is really just where we put an earthquake on a map. It's actually above the focus. So the focus of the earthquake is always underground. Sometimes it's not that far, oftentimes it's quite deep. And the epicenter is if you follow the focus straight up to the surface. I'll show you it on a diagram in a moment, okay? And then the fault is the fracture in the earth where the movement has occurred, and it's where movement is likely in the future as well. Again, the fault is a plane. It's a surface, like a two-dimensional surface. Here we have a very simplified diagram just showing two blocks. So we're talking about plates of the earth moving, or at least it doesn't have to be a whole plate, but two different sections of the earth's crust, let's say. Now you can see from the trees and the droid which side is the surface where you would sort of walk around. And we're not going to show how these blocks would extend in every direction, of course. Okay, this is a very simplified model. Well, when does an earthquake happen? When these two blocks are forced in different directions. Okay, so what I'm going to show here is when we get what is called a transform fault, when they are pushed sort of side to side with very little up and down motion. So watch what happens. The yellow block slides relative to the blue block, and there was an earthquake. While that was sliding, there was shaking going on. Okay, that movement caused the vibrations that we feel as an earthquake. And seismic waves are waves. So all of the things we've been talking about, waves, apply to them. So this location where the earthquake really happened, let's say it was only confined to these two blocks themselves, that's the center of the movement. That is what we call the focus. That is where the earthquake waves are coming from. The seismic waves originate. Boom, right there. But we can't put that on a map because it's underground, so we just follow it up to the surface and we plot that point on the map. That would be the epicenter. So you often hear in the news whenever there's an earthquake, you hear about the epicenter. Okay, but if you look up in a geology periodical, or if you look up the USGS website, which has the best information about earthquakes, okay, the US Geological Survey, well, they will show you the epicenter, yes, but they'll also talk about the focus and how deep it was. That can be of major importance, okay? And that is really where the waves originate, okay? But if you're at the epicenter, well, your chances are you're getting the strongest shaking. Almost always the epicenter experiences the strongest shaking from an earthquake, and so that's the place you hear about in the news. Now, to be honest, a fault plane is not always strictly a plane like you think of it, like a sheet of paper, like a flat surface. It can actually be curved. This is actually very, very common with faults. So it's a little more complicated than what I've led you to believe. However, the focus is always underground, like I said. The seismic waves originate at the focus, and the epicenter is directly above it. The reason I'm showing you this diagram is so you can see how the epicenter does not always appear to be on the fault line. See where it says fault scarp? That's where we would see the fault on the surface on a map. But because the fault can be at an angle underground, the epicenter does not always appear to be on a fault. Get it? So sometimes you can see a fault just by the displacement that has occurred. You can see this grove of orange trees has been offset. They call it offset. And if you follow the line where they're offset, it's just like that. One side has moved to the left. The other side obviously has moved to the right. And it's really hard to say which side has moved. In fact, it's almost impossible to say which side has moved. So in geology, what they do is they only consider the relative motion. They don't worry about getting into like, well, which side are we going to say moved and which side stayed still? Neither side really stayed still. They both moved in opposite directions, okay? And this is called shear forces, where they're going in opposite directions, like the sides of scissors or shears, right? They're going in opposite directions. And the way that geologists would describe this fault would be left lateral. So you might say, well, why would they describe it as left lateral when clearly the bottom side is going to your right? Well, this is the nifty thing they came up with. Geologists are usually out in the field measuring things. And they said, well, if I walk up to a fault from the side and I step over it, and the block I'm stepping onto is moving to my left, well, then I'm just going to call that left lateral. Okay. If, however, the block I was stepping onto moved to the right, I would call that right lateral. It's a very simple method, and it works really well. Okay. So notice if you were going the opposite direction, that little bent arrow, let's say he was coming from the other side, and he stepped over the faults, well, then it would still be going to his left from his perspective. Okay. Or if you were walking in those trees, from your perspective, it would be going to your left. So it's a pretty practical application. And it's really because you can never absolutely say which side is moving. They're both moving relative to each other. So obviously there have been many earthquakes along this fault to cause this kind of offset. It wasn't caused by just one earthquake. It was caused by many. What about if that offset goes on for millions of years? Oh, I don't know, let's say 30 million years? That's a long time. 30 million years, okay? That is 3 with 7 zeros after it. That's a long time, right? Well, what do you get after something like that? You get something like the San Andreas Fault, which runs most of the length of California and also the length of Baja California in Mexico, the whole peninsula, okay, both of the states in Mexico. So the San Andreas Fault is interesting because in general, well, this kind of fault is actually kind of the safest kind of fault. It's what we call a transform fault, okay? But if you notice, there's a little bit of a problem there. Notice how it's very, very straight at one end and very, very straight at the bottom, but there's that little kink in it, that little bend in it. Oh, and see that yellow dot? That's poly. That's where we go to school, well, if we're not doing distance learning. So that little bend is really what causes a lot of the problems in California, especially Southern California. That little bend, look around you. If you go outside with your mask on, look around and look at those mountains. There's some mountains around, right? Or the valley, you're in a valley, right? The reason that is there is because of the bend in the San Andreas Fault. You could chalk up most of the topography in Southern California to that little tiny bend in the faults. Interesting, okay? And if you notice all of those other red lines on there, those are other faults. So the San Andreas Fault is a huge, big transform fault. It's a huge plate boundary. And the way it's moving is like this. So would that be left lateral or right lateral? Think about what I just said before. If you stepped over the faults, which direction would the block you're stepping onto be moving? It would be moving to your right. So that is what we call a right lateral fault. And if it was just the San Andreas Fault, if it was just a right lateral fault, it wouldn't be such a big deal, but it has that bend in it. That causes problems. And all those other little red lines are other faults. Those are subsidiary faults. So these earthquakes don't only occur exactly at the plate boundary, which is the San Andreas Fault. That is the plate boundary between the Pacific Plate and the North American Plate. By the way, we're on the Pacific Plate, if you didn't know that. We are not on the North American Plate geologically. And that is where a lot of earthquakes happen, but they also happen nearby on subsidiary faults. So they can happen not always exactly on the plate boundary, but nearby. So here's a close-up of the greater Los Angeles area. That blue line is the San Andreas Fault. So what's the closest the San Andreas Fault comes to Pali? Well, if you go over the mountains and come down into Palmdale, boom, the second you get down from those mountains, notice how it gets very flat very quickly. That is the San Andreas Fault, right where the mountains meet the Antelope Valley, right there, okay? So that's not super close to us, really. If you think about it, it's on the other side of a mountain from us, but that doesn't mean that the earthquakes always happen over there. They can happen on the faults that are located in the San Fernando Valley, around Greater Los Angeles, all over the place. And by the way, let me just mention that these are the faults that we know about. Some faults are very, very difficult to find, notoriously thrust faults, very hard kind of fault to identify. And the Northridge earthquake actually occurred on a thrust fault that we had never seen before. So we don't even know all the faults. It's kind of sad to say. And if you were to go over the mountain and come down into Palmdale, well, guess what? The block you're stepping onto would be moving to your right. So it's a right lateral fault. So yes, I guess, well, Los Angeles doesn't always look like this. We don't get snow in the mountains that much of the time. Well, we do. It should be coming soon, this time of year, you know, January, February, rainy season, at least when it actually rains. So it's kind of pretty when it looks like this, but think about the whole reason that those mountains are even there in the background to give that backdrop is because of the bend in the San Andreas Fault. It causes the whole area to compress kind of like an accordion. And some places go up, some places go down. So the Los Angeles Basin, okay, is one of the parts that went down. The San Fernando Valley is one of the parts that went down. The Santa Monica Mountains is one of the parts that went up. The San Gabriel Mountains, the San Bernardino Mountains, those are parts that went up. Those are all caused by the bend in the San Andreas Fault. So this area, because of that bend, experiences compression. It folds up and it folds down, kind of like an accordion. If you don't know what I mean when I'm talking about an accordion, they have kind of gone out of style. I guess Weird Al still uses one. They used to be much more popular. My uncle used to play one. Okay, and here's a really fancy one. Oh, look, it's the Corona 2. I hope we don't have Corona 2. Oh, man. Corona 21 or whatever it would be. Anyway, let's not forget I said that. So an accordion, of course, goes, if you look at the corrugation, it goes up and down and up and down in the middle. Let me zoom in. So see how that goes up and down and up and down. And you can squeeze it together and pull it apart. If you pull it apart, it flattens out. That isn't shown here. And if you squeeze it together, they fold up. So that's what Southern California is like. We're like an accordion. We're living on the top of a giant metaphorical accordion here. And the San Fernando Valley is one of those places where it drops down. The mountains on either side are one of those places where it goes up. By the way, the San Fernando Valley would be much, much deeper, like a proper, real valley. Like you're thinking of a valley, you're picturing something that's deeper and sharper. Well, it would be if it hadn't been filled in by all the erosion from the mountains around it. So there's actually been a lot more change here than it appears because the mountains have been pushed up higher, but they've eroded down. The valley was pushed down deeper, but it's been filled in. So there's been much more of this accordion folding than is obvious to your eye. Well, don't forget Northern California and the Bay Area. Well, their big problem is they don't have a bend in the fault necessarily. They have a split in the fault where the fault divides into two sections that run on either side of the San Francisco Bay. The other problem is that the San Andreas Fault runs just outside the city of San Francisco. Notice the city of San Francisco, that line just to the left of it, that is the actual San Andreas Fault. And notice, compared to Southern California, it doesn't run that close to any major city, okay, as it does in Northern California. So that's the reason that we sometimes associate it with Northern California, even though Southern California kind of has the bigger problem, geologically speaking. Now, there is something called the Richter Scale. Guess where the Richter Scale was invented? California and in Southern California. More specifically, it was invented by a scientist named Richter at Caltech in Pasadena, okay, next to Pasadena. So the Richter scale is a way of measuring earthquakes, and it has been somewhat replaced by the moment magnitude scale. But I think the Richter scale is an interesting thing to talk about because it's a great way to examine logarithmic scales. A lot of people think that logarithmic scales are difficult to understand, but actually they're pretty simple, at least when it concerns a straight logarithm, okay? And in this case, the Richter scale kind of is, at least when we're talking about shaking. Now you're going to notice in your textbook that they go into detail about the energy of an earthquake. Well, that is a little bit harder, not too much harder. But what I'm talking about here is the shaking from an earthquake, which is what it was originally intended to measure. Because that's something you can just see on paper. If you look at your seismograph, you can see the shaking going onto the seismogram, onto the paper. We'll talk about that in a moment. So the Richter scale is a logarithmic scale. So when you hear about an earthquake that is a magnitude 6 earthquake, right? And you've been in a magnitude 5, you'd say, well, that's just one more. 6 is just a little more than 5. But actually, if it's a magnitude 6, that means it's a magnitude greater. That means it has experienced 10 times as much shaking as the one below it. And if you're talking about energy like they do in the textbook, that would be about 32 times as much energy was released in the earthquake. Okay, but I'm going to stick to shaking because I think that's a little bit more visual. So if you're comparing earthquakes, like a magnitude 10 earthquake, well, by the way, we've never measured a magnitude 10. Doesn't mean they can't happen. We just haven't measured one yet. They've gotten pretty close. We'll talk about that in a moment. If you want to compare a magnitude 10 to a magnitude 4, you might say, well, that's like 6 more. So that's, it's a lot more, but not crazily more, maybe like a little more than double. That's what it looks like. But no, remember, a magnitude 5 earthquake would be 10 times the shaking of a magnitude 4. A magnitude 6 earthquake would be 10 times a magnitude 5. A magnitude 7 would be 10 times a magnitude 6, and so on. So you have to multiply by 10 for every difference you go up. So magnitude 10 is going up by 6 magnitudes. 10 minus 4 is 6, right? So if you multiply by 10 6 times, what you wind up getting is 1 million. Okay, a 1 with 6 zeros. Think about scientific notation, right? 10 to the 6th power. So if you want to talk about how much more shaking there would be in a magnitude 10 earthquake compared to a magnitude 4 earthquake, and by the way, a magnitude 4 earthquake, you are going to notice if it occurs, a magnitude 10 earthquake would be 1 million times more. So it's crazy how much stronger that would be. Let's do one more comparison. What about a magnitude 9 compared to a magnitude 5 earthquake? Well, that's only a change of 4. But remember, that would be 10 to the 4th power, 1 with 4 zeros after it, okay, 10,000 times stronger. So a magnitude 9 earthquake is 10,000 times, that's a myriad, stronger than a magnitude 5 earthquake. So just keep this in mind. And again, I'm talking about the shaking. If you want to calculate the energy, well then it's for each change of magnitude, it's to the 10 to the 1.5 power. And so you can have fractional exponents, and I don't usually like to go into that if I can avoid it. But it turns out if you take 10 to the 1.5 power, that turns out to round to 32, okay? So every time you change a magnitude, it winds up being 32 times more energy. And that's the kind of question they're asking about in the textbook. You're going to see that in the textbook, okay? And they talk about the moment magnitude scale, which is also a logarithmic scale that measures earthquakes. Now, when an earthquake occurs, it releases more than one kind of wave. This is why I really wanted to get to this topic when we're in our waves unit. 2 of the waves that it releases are called P waves and S waves. Now, geologists have their own way of talking about things, their own terminology in general. They like to be different. And what does the P stand for? Well, actually, it doesn't stand for anything. What does the S stand for? It doesn't stand for anything. It's just a symbolic letter. But fortunately for us, there are words that begin with P and begin with S that kind of match up with those waves. So some people would say the P wave is a pressure wave, okay? And the S wave is a shear wave. Another thing you could say is that the P wave is a primary wave and the S wave is a secondary wave. You know what? Because both of those things are true. That's true. But that is not actually what the P and the S wave mean. They're just symbolic letters. So when an earthquake occurs, it always generates both of these kinds of waves, okay? And these are called body waves. They actually travel through the ground, even though it doesn't necessarily show that in this picture. They don't just travel along the surface, they travel through the body of the Earth. Think of the body of the planet Earth. But they travel differently. So let's examine them. Remember when we talked about longitudinal waves and transverse waves? Well, guess what? Same thing. But geologists like to describe them differently, okay? They like to describe them as P waves and S waves, okay? So a P wave is a longitudinal wave, and an S wave is a transverse wave. They can also be called shear waves because they have some side-to-side or up and down motion, okay? Well, these waves, even though it's not clearly shown in this diagram, travel at very different speeds, okay? The P wave, because the compression is in the same direction the wave is moving, moves along very rapidly. But the S wave has to sort of wait for the material that it's traveling through, the medium it's traveling through, to shift to the side and sort of snap back. That slows it down quite a bit. So the basic thrust of this, and there is a thrust fault, is that P waves are faster than S waves. So if they're both produced at the same place at the same time, they will separate and travel at different speeds. The P wave will get further and further ahead of the S wave. This is how we locate earthquakes, based on the P waves and the S waves. So again, a P wave is a longitudinal wave. You can think of it like a pressure wave or a primary wave. And the particles are being compressed in the same direction the wave is moving, which is why it's longitudinal, and they travel real fast. An S wave, on the other hand, involves side to side, up and down, or both kind of motion, which slows the wave down, and it's kind of shaped like an S if you turn your head sideways, the movement, so that's a good letter to use here, and they take a while to travel. This also travels through the ground until it reaches a liquid like the outer core, and then it dies out. Surface waves actually do the most damage, but they don't travel very far from the earthquake. They're not very useful for locating the exact position of the earthquake, either the epicenter or the focus below it. But they do kind of give you a sense of where the earthquake happened, like in that area, because that's where all the surface waves did all that damage. And they can involve lots of different kinds of motion, different kind of waves that are sometimes more analogous to the waves we find in the ocean, okay, sometimes. And surface waves only occur at the boundary between the land and the air above it, or the ground of the ocean floor and the water above it. They don't travel very far from the earthquake unless it's a massive earthquake. So how do we measure earthquakes? Well, we measure earthquakes with various kinds of seismographs. Seismographs measure shaking. That's what they do. There's a bunch of different designs. There's electronic designs. This is an old-fashioned one shown in this picture. It's basically just a pendulum. Oh yeah, we were studying pendula. A pendulum, very heavy pendulum, with a pen on the bottom, hanging over a spool of paper that is turning at a steady rate. So if the pendulum starts swinging, it's going to record that on the paper. You'll know when it occurs because there's a timestamp. Okay? Remember, pendula don't stop immediately. They die down. So remember, whenever a pendulum begins shaking, you got to give it a minute to die down. That's what you usually see when you look at a seismogram. A seismogram is the recording made by the seismograph. So there's the seismograph, which is like the instrument itself. And there's the seismogram, which is the recording. So the seismogram will record the P wave. But because P waves are compressional waves, okay, they're longitudinal waves, they don't actually cause that much shaking. What they cause is like a jolt. And then following the P wave, your seismograph will record the S wave. And if you're close enough to the location of the earthquake, you might also receive the surface waves, okay, which are the ones that are probably going to cause the most damage, okay? But there is a mathematical relationship between the P waves and the S waves, the speed they're traveling, and how far they separate, and that is what we use to locate earthquakes. So I think this is pretty cool. We use seismic waves for so many different things. We obviously want to locate the earthquake. We want to know where it happened and why. And it also helps us examine the earth beneath our feet. This is really how we know a lot about the earth, is from these waves. So they're very, very useful. And we just have to sort of wait for them to happen. Okay, you have to sort of wait until the earth generates them. So notice that the P wave on this little seismogram is a very tiny little blip, and then it dies down. The S wave is significantly more because it involves up and down, side to side motion. In order for your seismograph to work well, it has to be very isolated from other shaking. Because obviously if you're near a road and trucks are driving by, well, that's going to cause shaking too. If a person stomps by on the floor, that's going to cause shaking too. So generally we try to locate seismographs in isolated locations, okay? Places that are not going to experience very much other shaking. One place you can locate a seismograph is in a pit deep underground in what we call bedrock. Bedrock is like solid rock as opposed to like just erosional rock, like alluvium that is washed off of mountains. So it's generally less likely to just be shaking randomly or to slide around. And if you do that well enough, put it out in a forest, far from where people are, far from a road, you're probably only going to record the seismic waves from earthquakes. So here's a quick description, a little chart about seismic waves. There are the P waves, which are the first waves to arrive. And that goes for anywhere you are. Okay? The only place they would arrive simultaneously is if you are exactly at the focus, which would mean you are underground. So it's not going to happen. So you can think of P waves as being primary waves, like the first waves. Pressure waves, which they are very much like pressure waves. They're compressional waves. And they are the first to arrive everywhere. They go through the entire Earth. Then there are S waves. Well, it's good that they use the letter S because they do look more like sinusoidal waves, like the shape of the letter S. They can be thought of as secondary waves or shear waves. These are the second to arrive everywhere, again, unless you're at the focus. Now, these S waves don't travel through the Earth's core, which is interesting. That tells us something, okay? And then if you're close enough to the source of the earthquake, well, then you got your surface waves. Those travel at the boundary, okay? Just like waves in the ocean, they travel at a boundary between two media of different densities, okay? Now, they're only near the source on land, but if you generate a tsunami, that is the only time that surface waves can travel far. And then the distance they travel is great. It's huge, okay? But unless it makes a tsunami, surface waves are generally limited to within a short range of the epicenter, which is right above the focus. And obviously surface waves don't go to the Earth's core, they just stay on the surface of the Earth. So look closely at this seismogram and you'll see the beginning of the P wave and the beginning of the S wave. Let's ignore the surface waves for now. This diagram is showing separations of 1 minute. Every one of those lines on the seismogram is a 1 minute interval, and the dark red lines, the darker bold red lines, are 5 minute intervals, okay? So how can we use that to determine the earthquake? Well, if you know how many minutes pass between your P wave and your S wave, or even if you're closer, how many seconds pass, you can tell how far you are from the earthquake. The only problem is that doesn't tell you which direction it was. That doesn't tell you if the epicenter was east of you or west of you, north of you or south of you. So how do you locate an earthquake? This is interesting. What you need are seismograms from 3 different locations on Earth. That is minimum. As long as you have 3 or more is better, by the way, you can locate any earthquake anywhere on Earth, okay? You may notice if you first hear about an earthquake on the news, they almost always misreport its location by a small distance, okay? For example, the Northridge earthquake happened in Reseda. Okay. The San Fernando earthquake happened in Silmar. You know, they always like just mislocate it by a small amount. That's because their first report is based on fewer data points. And then as you get more and more data, well, then you can locate the earthquake more precisely. Okay, so I'm going to show you how they use this really quickly. This goes for an exercise that we would have normally done if we had a few more days. We would have done a little lab about this, but we're short on time, so I'm just going to show you how we would do it. Okay, so here we have 3 seismograms from the same earthquake. It's important that they're about the same earthquake. Let's use the one from New York City. Okay, in New York City, here's a little bar representing the number of minutes. It looks like 1, 2, 3, 4, 5.5 minutes. So there's a 5.5 minute interval between the P wave and the S wave. But that doesn't tell you like how long ago the earthquake happened. All you know is when you get the waves. So all they can tell is the spacing between the P wave and the S wave. And then they go to their handy dandy little chart, their little table, and they look at what 5.5 minutes is on this table, figure out where the earthquakes would be 5.5 minutes apart. Turns out that would place you about 2,400 miles away from the earthquake, or pretty close to 4,000 kilometers from the epicenter of the earthquake. Okay, 4,000 kilometers. Okay, so now you know the earthquake is that far away from New York City, and if you did the same thing for Seattle, you'd find how far it was from Seattle. Do the same thing with Mexico City, you'd find the distance it was from Mexico City. Then you go to your map, and you measure that distance. What do we say, 2,400? Well, it could have been east of New York City. It could have been west. It could have been north. It could have been south. It could have been in any direction. So what we really have to do is make that into a circle. Okay, usually on a paper map, we'll use a compass, or on a computer, we can put a circle there. And basically notice, we know the earthquake happened somewhere on that circle, right? And then if we get information from Seattle and information from, oh yeah, before I put in Mexico City, notice that those circles overlap in 2 places. So we know that the location of the earthquake is either the one way up in Canada or the one down in the Sea of Cortez in the Gulf of California near La Paz there. Okay, we don't know which one until we get our information from Mexico City. Oh, now we can see that they're all very close to overlapping right there. So that would be the epicenter of the earthquake, right inside that little position there. Now, really, those should all match up exactly, but often they don't for various reasons. So we would get more information, more than just 3. We get 4 and then 5, and then we get it more and more exact, and then we know its exact location. Okay, and also we'd be able to tell its depth, it's where the focus was. So we can put an epicenter on the map this way, and then we can also find there's other ways of measuring the depth to locate the focus. Okay, so this is not perfect also because of the kind of map we're using here. You would actually want to do this on a 3-dimensional globe to get it right. But this is called triangulating an earthquake. Why is it called triangulating when it doesn't really use triangles? It uses circles. Well, look at those 3 cities. Notice how there are 3 of them. They make a triangle. And it works a little bit better if those are very spread out. If 2 of the cities, if 2 of the locations were very, very close together, it would be less accurate. So that is how we locate an earthquake, based on the timing difference between the P wave and the S wave on a seismogram recorded in 3 different locations. Isn't that cool? Isn't that neat? The other thing that seismic waves will tell us is what the Earth is made of, because P waves travel right through the Earth to the other side. You can actually receive P waves from an earthquake that literally happens on the opposite side of the planet. Now, the opposite side of the planet from us is the bottom of the Indian Ocean, by the way, in the southern hemisphere. And there can be earthquakes there. So if there's an earthquake there, we'll get it right here. P waves have no trouble passing through solids, liquids, or gases, or even plasma, actually, but not that there's plasma in the Earth. So they travel right through all the layers of the Earth. However, S waves don't. S waves travel through quite a bit of the Earth. In fact, you can get the S waves for an earthquake on more than half of the planet. Just a little bit more than half of the Earth will receive the S waves from any given earthquake. So they travel through what is called the crust of the Earth and the mantle of the Earth. Okay? But what they don't travel through is what we call the core of the Earth, the heart of our planet. So why don't they? Well, this actually tells us something about the core of our Earth. Okay? Because S waves travel very well through solids. Very, very well. Because solids don't want to budge. They'll snap back into position. But they don't travel very well through the body of a liquid. Okay, now you might say, wait a second. Aren't those S waves on the surface of the ocean? Not exactly. Those are surface waves. Okay, there's a big difference of density there. S waves will not travel through the body of a liquid, not even the ocean. Okay, so when they get to the core, they die out. That tells us that the core of the Earth, at least part of it, is a liquid. Isn't that amazing? That way below our feet, 2,000 miles, 3,200 kilometers below our feet, okay, is a liquid, a very, very dense molten iron core of the Earth. Crazy to think that some of what is below our feet is actually liquid. And we know this for a fact because of the way the waves travel through this. We also know that it's made mostly of iron because of its density. How do we know its density? Because of the P waves that travel through it. How fast they move through it tells us the density. You can tell the density of a material by how quickly waves travel through it. So looking at these seismic waves is kind of like looking at an X-ray of our planet. By the way, that whole dark brown portion on the bottom there, where the S waves do not travel, I mentioned this earlier in earlier notes, is called the S wave shadow. It's sort of the shadow of the core of our Earth. That part of the planet doesn't receive S waves. So you can't use that handy-dandy trick we use to locate the earthquake if you've got data from the opposite side of the planet, because it won't have the S waves. It'll just get the P waves, and with those alone, you cannot use that technique. So what I did not mention when we were triangulating the earthquake was that you do need data from 3 locations that are basically on the same half of the planet that the earthquake occurred. So here we see an X-ray overlay. It has these are actually several images superimposed on each other of a human head. So notice the X-rays allow us to see inside what we cannot normally see through. Well, that's what seismic waves are like with the Earth. Imagine that the Earth is that head, and we're able to see what's inside it using seismic waves. Pretty neat, right? So now we know what the Earth is made of because of which waves travel through it, how long it takes them to travel through it. It's really because of these seismic waves that we have so much knowledge about the inside of the Earth. We actually have very detailed information putting together the data from all different seismic waves. And this was a diagram from your textbook, and it shows you the velocity of the earthquake waves, which of course directly relates to density. So notice on the left it says velocity, on the right it says density. It's using the same scale there, right? And obviously one layer of the Earth doesn't all have the same density, but it's pretty consistent within each layer, and then there's usually an abrupt change when you get to a new layer. Like when you go from the mantle, which is sort of the beige area, or the kind of orangish area, to the core, which is sort of the yellowish area. You see there's a big sudden change in density occurring right there. So now we know that the Earth has many layers, and this is part of the way that we understand how the Earth changes. Understanding the crust, the mantle, the 2 layers of the core, the inner and outer core. And on the right side, you can see the other way we chop it up. If we're going to get more technical, there's the lithosphere, the asthenosphere, the mesosphere, the outer core, and the inner core. But we usually only get into that if we're getting very technical about geology. But this is a pretty good diagram. The textbook did a good job selecting these particular diagrams. So the only way that surface waves are going to travel very far from the source is when they generate a tsunami. So you probably have heard about tsunamis. People used to call them tidal waves. They are not tidal waves. They are not caused by a tide. So we've been trying to phase that out, get rid of that term. But you still hear it. You might have heard tidal waves. That is actually a tsunami. Tsunami is a Japanese word, and it means exactly what it means in English. Okay? Generally, tsunamis are made by earthquakes. So it's a very simple idea. If you have an earthquake on the ocean floor, and if part of the ocean floor moves up, that pushes up the water very suddenly, like a jolt. And then that makes a wave. Now, the thing about seismic waves is that they happen very suddenly. There's one event that triggers them. And then that tsunami travels out based on the speed that that fault block moved. Well, often that can be at hundreds of miles per hour. Very frequently, it's approaching the speed of sound, approaching something like 500 miles per hour, maybe 800 kilometers per hour. So those waves travel out in all directions. And they have a very long wavelength, because think about the wavelength. The block moves up, the wave rises, and then it shoots out at 800 kilometers per hour. So by the time the wave comes back down, it's traveled very far. There's a very long wavelength. Remember what we said about ocean waves, that they start scraping on the bottom? I don't think we got to this part, but how they only affect 1/2 wavelength of depth? So that becomes a big problem when you're talking about tsunamis that have an extraordinarily long wavelength. Even though tsunamis generally, when they start out, have a very low amplitude. Some of them are only 3 feet, 6 feet, okay, 1 meter, 2 meters in height, let's say. The problem comes when a tsunami gets to shallow water. When a tsunami approaches the land, gets to shallow water, well, because it affects 1/2 wavelength depth below it, well, then part of that begins to drag on the bottom. Okay, part of that affected area begins to be slowed by the ocean floor, causing the tsunami to slow down. So when you have a wave traveling at that tremendous velocity, and suddenly its velocity is grinding to a halt, that increases the amplitude. The energy from the wavelength gets transferred vertically into the amplitude of the wave. So suddenly, rather than having a super fast, very low wave, you have a slower, much taller wave. Okay, so depending on the way that the tsunami is slowed down, this is what causes the damage when it hits the shoreline. Okay, so a tsunami can wind up being 10, 50, 100 times taller than it was out in the deep ocean. Okay, that's why tsunamis often cause the worst destruction from an earthquake. Very typically, when an earthquake generates a tsunami, it's the tsunami that does most of the damages and unfortunately takes the most lives. And if you look at this map, there's an awful lot of these earthquakes that are going to occur under the ocean. So the ones that occur under the ocean are the only ones that are likely to make a tsunami. But there are many, many, many. And once it generates a tsunami, well, there's almost no limit to how far that can travel. It can travel across an entire ocean. So it can travel for many thousands of kilometers, many thousands of miles. I've been using miles a lot more in these notes than I usually do. It's interesting. Okay. So 2004, okay, up until that point, there had never been an earthquake this big in my lifetime. There was a magnitude 9 earthquake in Indonesia. That generated a tsunami that struck many, many countries in the area, all around the Indian Ocean, and it killed something like 50,000 people. They never really got the proper death count because some towns were just obliterated. So when an earthquake happens under the ocean, generating a tsunami, that is a big problem, okay? And then just 7 years later, okay, there was another one, okay? So 2004, remember that date, generated a tsunami off Indonesia, traveled across the Indian Ocean. It even reached all the way to Africa. Did a little bit of damage over in Somalia in Africa. So when you talk about earthquakes, we've got some famous ones. Like in California, there was a famous earthquake back in 1906 that pretty much destroyed San Francisco. You may have heard of the 1971 San Fernando earthquake. Okay, that also did quite a bit of damage. That was a valley earthquake back in the early 70s. You may have heard of the 1989 Loma Prieta earthquake up near Santa Cruz that did a huge amount of damage in Northern California. And you have definitely heard about the Northridge earthquake in 1994 that happened in the San Fernando Valley, doing major, major damage. Well, this is the kind of earthquake we get in California. Notice that most of these are in the magnitude 6 range. The 1906 earthquake is estimated to be 7.8, but we don't actually know because that's actually before they had really accurate measurements. That's about the best we can do in measuring that one. But those pale in comparison to some of the earthquakes we've had around the world. For example, in 1960, there was an accurately measured earthquake in southern Chile that was 9.6. So far, that is the largest earthquake that we have accurately measured. Now, that doesn't mean that is the greatest earthquake of all time. It's just we've only had instruments, for less than 100 years. So in that time, that's the greatest earthquake that has occurred. Okay? It doesn't mean there could not be a 10. We just have never recorded one. Okay, so notice that the San Francisco earthquake and the Loma Prieta earthquake were about 83 years apart. That's a pretty good spread. And then the San Fernando earthquake and then the Northridge earthquake, they were about 23 years apart. So some people read into that and they say, well, if we had an earthquake 23 years apart, then we should have another earthquake 23 years after that one, and that would have placed it in 2017. So that's why people are always saying we are overdue for the next San Fernando Valley earthquake. They say that all the time. But geologically, earthquakes don't really happen like that. They happen sporadically. They happen in clusters. Sometimes there's a big pause between earthquakes. But we really should be prepared, definitely, for earthquakes of that variety, of like the upper magnitude 6 range. We're bound to get one eventually in the San Fernando Valley. We hope to never get a magnitude 7 earthquake, but it's possible. We are unlikely to ever get a magnitude 8. That seems out of the question. But then again, geologists have been wrong before. There was a devastating earthquake in Haiti in 2010. You might have heard about. It caused huge damage. Partly it was because of the earthquake happening so close to the city Port-au-Prince, but also it was because of the building regulations in Haiti, which are not as stringent as they are in California, for example. Okay, but a magnitude 7 earthquake can do major damage, even here if it happens near an urban area. A lot of the biggest earthquakes you hear about happen off the coast of South America. For example, here's another 2010 one. There was a magnitude 8.8 off the coast of Chile. That's not far from where that magnitude 9.6 happened in 1960. These actually happen off here pretty frequently, and they happen under the ocean. They are very likely to generate tsunamis that can travel all the way across the ocean. Oh, what I forgot to mention is that 1960 earthquake generated a tsunami that traveled all the way to Japan on the other side of the ocean. Almost the other side of the whole planet, really. And then in 2011, okay, there was another 9.0. So remember, I was born in the early 70s, right? There were no magnitude 9 earthquakes in the 70s. There were no magnitude 9 earthquakes in the 80s. None in the 90s. Okay, and then in 2004, we had one. And then only 7 years later, there was another one. And nobody, by the way, expected Japan to ever get a magnitude 9. So here's an example of geologists having misestimated the risk. They thought Japan would maximum receive a magnitude 8. This had never been seen in Japan before. This is the largest earthquake in Japanese history. And of course, it generated a tsunami. The tsunami is what caused all the trouble in Fukushima, okay, which I think should be like the new swear word. Fukushima. You can say that in polite company because it's a city in Japan, but it kind of sounds like a bunch of curses stuck together, right? It caused pretty much a nuclear power plant to essentially partially melt down. Okay, that was caused by the tsunami, which was caused by the earthquake. The tsunami from this earthquake, well, it could have reached California, but the way that it traveled, it actually dissipated. It was recorded in California, but it was minimal. It did do some damage in Hawaii, though. It did reach Hawaii and do some damage to the coastline. And that's why I made this poster. I originally made this one as an example of something macroscopic and microscopic, but then it occurred to me that Godzilla was really a metaphor for nuclear power, and it was a nuclear meltdown in Fukushima, and it sounds kind of like a curse. I made this one right after the accident occurred. It hasn't really caught on. I haven't heard too many people saying Fukushima. I guess you should be careful when you say it, because then people might misunderstand you. But anyway, watch your mouth. So luckily, the magnitude 9 earthquakes are very rare, and they're unlikely to happen anywhere near us. The closest place they might happen is up near, closer to Seattle, up in Washington State. There is a possibility there. But again, people didn't expect it to happen in Japan. So remember, there have only been 2 magnitude 9 earthquakes in my whole lifetime, right? In the whole world. So in the whole world, though, every year there's 1 million earthquakes. So how does that make sense? That's because if you notice here, this is the moment magnitude scale, the one they talk about in your textbook, similar to the Richter scale, also logarithmic. Most of those earthquakes are less than magnitude 2. Notice at the top, the ones that are less than magnitude 2, there's about 600,000 around the world. So if somebody tells you there was an earthquake, you better follow up and say, well, what was its magnitude? And then ask where was the epicenter. Because there's always an earthquake. Every day, there's many, even in California. But you got to talk about of which magnitude. Notice how they get increasingly less common. So when you get to earthquakes that you're really going to notice, like a magnitude 4, there's only 13,500 in the whole world, and some of those are under the ocean, of course. And they get increasingly less common as you go to the higher magnitudes. Okay, so usually the ones we worry about, if it's a magnitude 6 in a populated area, if it's a magnitude 6 in the desert, honestly, you probably won't even hear about it in the news. Or if it's a magnitude 7, pretty much almost anywhere, you'll probably hear about it. Magnitude 8s are very noteworthy, and they don't even happen on every given year. And those are the ones that we worry about creating tsunamis. Magnitude 9s, just all bets are off. Forget about it. Okay, but the kind we expect to get is sort of in the magnitude 6 range. That's what we are expecting, not looking forward to, but bracing ourselves for. Even something like a nuclear test will be detectable by a seismograph. Like North Korea, unfortunately, occasionally does nuclear tests. Here's an example of one of their tests. That's what that blue square is. That's a magnitude 5.1 earthquake. So some earthquakes are man-made. There's also been the recent development of hydraulic fracking, particularly in the state of Oklahoma, that has been triggering many, many minor earthquakes. Okay, so some earthquakes can actually now be generated by humans or by inadvertently as a side effect of what people are doing. Okay, up until recently, this was not the case. Earthquakes obviously do a lot of damage. We try to prevent that by the way we make our buildings. They do a lot of things. Every time there's an earthquake, they examine what went wrong, and they try to retrofit the buildings. That's one of the things they're doing, by the way, at Poly right now. One of the things they're doing with the construction is they're retrofitting buildings. Like, you really shouldn't use bricks. Bricks don't fare too well in an earthquake because once they separate, they don't go back together. Those cracks get bigger and bigger. So bricks is something we try to avoid, unless it's just an edifice, just a surface brick, not structural. Even then, they're likely to crack and fall apart. Liquefaction is also a big issue in earthquakes. If you shake the ground at the right frequency, it turns out the ground, especially if it's wet, can act like a liquid. If you vibrate the ground, it can jump around. Like if you jump a pit, if you jump a container, vibrate a container full of sand, then things will sink into it. Well, the same thing goes with the ground. Unless it's bedrock, buildings will sink into the ground. This is another thing that occurs, especially when the ground is wet, but actually it can occur to some extent even if the ground is unconsolidated and dry. And it's called liquefaction because the ground is made into essentially a liquid. Okay, temporarily it acts like a liquid. So this was a big issue in the Northridge earthquake. Northridge earthquake, you probably heard about back in '94. This is the kind of damage we're trying to prevent with all of our retrofitting. Freeways collapsing, okay, buildings sinking into the ground, all kinds of things like this. Now, hopefully the next earthquake we get will not have this exact same kind of damage, but it's really hard to prevent completely. And of course, if we get a magnitude 7 or above, then it's almost like all bets are off. Everything we've planned for is probably not going to hold up as well as we think. So these earthquakes have been happening in this sort of area for 30 million years, and they're not likely to be stopping anytime soon, which is why living around here, we always need to be prepared for the next earthquake. I mean, I know we have enough things to worry about, but we can't forget about the potential for us to get. We should at least be prepared for an upper magnitude 6 earthquake in the San Fernando Valley for sure. So sorry to end on a bummer there, and sorry to go a little long here, but that's the end of the notes on seismic waves.